Greetings and welcome. In today's video, we're going to talk about solving quadratics graphically. And before we get to that, I have to talk about how do we graph quadratics. So what I have here is kind of a standard form of a quadratic equation. So it's f of x equals ax squared plus bx plus c. The f of x, by the way, could also have been written by y equals that. It just basically is another way of writing the output of the function. So the x squared term is our quadratic term, the x term is our linear term, and the c is our constant term. All right, and the graph of a quadratic is called a parabola, which is a smooth curve. It's not exactly U-shaped in the sense that it's actually getting steeper and steeper, faster and faster. It never goes vertical. It doesn't come down to a V like an absolute value graph. So it's a smooth curve there. And the domain of it actually does go all the way to the right for infinity. So it does keep getting over, but clearly not as fast as it is going to positive infinity in this case, vertically speaking. So the domain is the set of all x such that x goes from negative infinity all the way to positive infinity. And the range just goes from your minimum point in this case all the way to positive infinity. Although it is also possible to have an upside down parabola function as well. So some of the significant values of the parabola, the minimum point is called the vertex. And we'll eventually have a formula to help us find that. Some other valuable information would be the x-intercepts, which are also sometimes called roots, and which are also called zeros sometimes. So those are also valuable to know. And then a third point that doesn't it would always exist, is the y-intercept. And what I want to point out is that the x-intercepts don't always exist. Sometimes it's possible to have a parabola that's all completely above the x-axis where it never touches it. It's also technically possible to have a parabola that ricochets off and touches at a single point. So that's kind of most of the valuable information there. Another thing about parabolas is that it has an axis of symmetry, where it's a mirror graph over this line. So this is called the axis of symmetry. And the equation of the axis of symmetry, it will always pass through the vertex. So it will just be the equation x equals, and then whatever the x-coordinate of the vertex is. So here's some valuable information about the graph. Eventually I'll also talk to you about the shape of a regular parabola, and that it has a quote-unquote slope that can be consistently found. So let's talk about this. So the first thing that is helpful to find out is the vertex, and there's a formula to figure that out. So I'll call this the x-coordinate of the vertex, v sub x, that's my own notation. Can be found by doing the formula negative b over 2a. Alright, so that's how you can find the x-coordinate of this vertex, or the overness of it. The y-coordinate of the vertex, what I would do is plug the x-coordinate in to my original function. And when I plug that in for x in both spots and evaluate, it will end up giving me the y-coordinate. So let me actually... So another way to say this is plug x coord into function and evaluate. So that's going to be the most valuable point to find. So the vertex then would be represented as whatever Vx was and whatever Vy was. So an ordered pair, right, would represent our vertex. Now to find the roots or x-intercepts, one of the ways we can do that is we can set the function equal to 0. So set f of x equal to 0 and solve. Which, I mean, we're talking about today solving by graphing, so I guess that would kind of be unnecessary if I was using that technique. But I do want to point out that when the function's equal to 0, that will give you the x-intercepts and also the solutions of the function when it's equal to 0. So it's kind of like this interrelationship going on there. Graphing can be used to solve if I was able to find enough other points, and then wherever it crosses the x-axis would be a legitimate way of solving a quadratic equation that's set equal to 0. However, I'm not necessarily a big fan of that technique, so mostly today we're just going to talk about how we could graph. So the roots would be end up being, there's potentially 0 roots, 1 root, or up to 2 roots. So let's see, so set function equal to 0. And solve. So this technique of solving could be done using the quadratic formula, factoring if possible, and then later on we'll look at completing the square in future sections as methods to do that. And the roots will be 2 points, so or up to 2 points, so you'll have x equals some number and x equals some other number. I believe that S1 and S2 is notation that's used in later sections of our text. Another way you could write it is S1 comma 0 and S2 comma 0, because these are going to also be ordered pair, and I just want to point out the y coordinate is going to be 0 for all of these because every point on the x-axis has 0 as a y coordinate since it didn't go up or down. The easiest point to find is the y-intercept, and that is going to be the point 0 comma c, where c is the constant term in our equation. Let's see, scroll up still. So that one's just a quick read. The way I think about this is if I was thinking of y equals mx plus b, our constant term in the slope-intercept form of a line was our y-intercept there as well. And actually that will be the case for any function. The constant term will be your y-intercept. So that's kind of a valuable little thing. Some other information that we can gather from the graph is, let's see, the direction that it opens. And the way you can figure that out is if a is greater than 0, the graph opens up. And if a is less than 0, the graph opens downward. And then as regarding the shape of the graph, I think this will require some further explanation. Let me draw a picture here real quick. So if I have a regular old parabola, one of the ways I can find points on it, let's say the vertex is at the origin. If I go up 1, over 1, that will give me another point from the vertex. So this point has to be the vertex, all right? And then from there, if I go up 3 over 1, and then up 5 over 1, these will give me consecutive points on my parabola for a regularly shaped parabola. And you can see it's getting steeper and steeper, faster and faster. The thing that I want to point out is that this 1, 3, and 5 are consecutive odd numbers. So this, the slope, quote unquote, of the graph are consecutive odd numbers starting at the vertex. So for a regularly shaped parabola, that is the case. So from here on, it would go up 7 over 1, and then up 9 over 1, up 11 over 1, etc. So that can be helpful for us to determine kind of a few points on the parabola once I've located the vertex. Now, it's possible that the parabola doesn't have a regular shape. All right, and one of the ways we can test that is if the absolute value of a is greater than 1. All right, so the magnitude of a is bigger than 1, so it's a number that's not a fraction less than 1. Then what that tells me is this is a vertical stretch to the graph, where basically it's going to be either doubling these 1, 3s, and 5s, or quadrupling the 1, 3s, and 5s, or multiplying it by 4.5. Any number that's absolute value is greater than 1 would be a stretch. And if the absolute value of a is less than 1, then it's a vertical smoosh, which is my own description, or you could consider that a horizontal stretch. And if you imagine what I would get if I multiplied each of these green numbers here by a half, for instance, it would result in the parabola growing half as quickly, and it would still be increasing steeper and steeper, faster and faster, but it would end up in a wider shaped parabola. So maybe at another point I'll do some further analysis on that, but for now that's all we need to know. So here's a whole bunch of information you can gather, all from the equation of the quadratic function. All right, so let's actually look at doing a problem. So let's see. So here's an example. So let's graph and find all significant info. And by that I mean find all of the significant points, such as the vertex, the roots, the y-intercept, and the axis of symmetry. And so let's grab a problem here. So what if I've got y equals, x squared plus 3x minus 18. So one of the things that'll be helpful, let's first figure out what is the values of a, b, and c. And I've had students in the past where they'll just say, like, a is this, b is this, and I don't recommend using those arrows because I don't know if you're referring to just the number or the whole term or the number and the sign. It's a little bit too vague. So let's actually define the value of a, b, and c. So the value of a is the coefficient of my quadratic term, and this one has a little 1 hiding there, like a hobbit wearing a ring. It was invisible the whole time. So a is 1, b is 3, the coefficient of our linear term, and c is our constant, including the sign, is going to be negative 18. So let's actually do some work. So starting off, I guess we could do the analysis based off of the a for starters. So let's see, since a is equal 1, it's a regular shape. Since a is positive, that tells me that it opens up. And I think that's most of the analysis we can get from that. So now let's find the vertex. So vertex. So we're going to first find the x-coordinate of the vertex by doing negative b over 2a. So that's negative 3 over 2 times 1, or negative 3 halves. I could consider that negative 1.5 if we wanted. The y-coordinate of the vertex, as I said, we then find by plugging this in for x in our function. Now here I labeled the function as y equals this, but if this was f of x equals that, I would just plug this in for the x value there. So I'm going to say f of negative 3 halves equals, and so let's just plug it in very carefully, and everywhere I plug it in, I'm going to carefully use parentheses here. So let's see, 3 is the coefficient here, times negative 3 halves minus 18. And in this case, it'll require a little bit of fraction work, but it won't be that bad. Let's see, a negative all squared is going to be positive. 3 squared is 9. 2 squared is 4, plus, actually 3 times negative 3 will become minus 9 halves, and then minus 18. And I'm going to need to find a common denominator in order to combine these. So between 4, 2, and 1, the LCD is 4. So I'd have to multiply this by 2 over 2 and this by 4 over 4. And let's see, so equals 9/4 minus 18/4 minus, let's see, 4 times 8 is 32 times 4 is 40, so that's what, 72/4? So let's see, combine these, 72 and 18, both negative, becomes more negative. It's negative 90, and then plus a 9, this is a positive term here, right? I believe is negative 81/4. Interestingly enough, it is a perfect square. So, so here's the y-coordinate of our vertex. So our vertex, in this case, is the point negative 3/2, comma, negative 81/4. And in this case, because I'm talking about a point on a graph, usually I'm always a fan of leaving stuff as improper fractions, but I'll write a decimal equivalent of this. So that's the same as negative 1.5, comma, and let's see, 4 goes into 80 20 times, and then a quarter left over, so that's negative 20.25. So here's our vertex. So that's our most significant point right there. To find the roots, what I would do is take the original function, which was the x squared plus 3x minus 18, and instead of having y equal this, I'm plugging in 0 for y, and I would solve. And the ways I would solve this is either by factoring, quadratic formula, or completing the square. So I believe this problem is factorable. The factors of 18 are 1 and 18, 2 and 9, 3 and 6, and which of those subtract to be 3? That would be 3 and 6. And so I'll have, let's see, x with a 3 times x with a 6 equals 0. And what do we got? They multiply to be negative, so their signs have to be the opposite of one another, and they add to be positive, so the more influential of these numbers must have been positive, so it must be a plus 6 and a negative 3. And now that I've got two things that multiply to be 0, I set each one equal to 0 and solve, and I'll get x equals 3 and x equals negative 6. And the way I would have done that was by adding 3 here and subtracting 6 there. Now, some students will incorrectly combine these as a single point. They'll say 3 comma negative 6, and that is not going to be correct. These are two separate points. Sometimes it might not even be a bad idea to think of that as 3 comma 0 and negative 6 comma 0. And let's see, the last significant point we can find is the y-intercept, which is the easiest to find. It's just 0 comma c, and what was c in our problem? Negative 18 right there. We can also see it here and here. So the y-intercept is just 0 comma negative 18. So to graph this, let's see if I've got, let's actually find the axis of symmetry, which I don't think I mentioned earlier. Well, I did verbally mention it, but so the axis of symmetry is always going to be a vertical line, and it passes through the vertex. So it's going to be x equals v sub x. So x equals, and what is the x-coordinate of our vertex? Negative 1.5 is the equation there. So let's see. To graph this, I'm going to pull this up on Geometer Sketchpad, which I don't have running yet, just so I can steal some graph paper. But this one won't be as pretty to graph because we've got some unusual points there, but that's quite all right. Let's see, open up a new sketch, cancel. And let's see, so here we go. Let's see, I just want to get a grid here real quick. And let's see, we go down as far as 20. Let's see, grid form, I want to put it on rectangular. right? Was it negative 20 1/4, something like that? And I think our y-intercept was at negative 18. Our x-intercepts were at 3 and negative 6. So horizontally speaking, I don't need that much space. Let's see, hide that point, and let me just grab a snapshot of these axes. And let's plot this, so paste. So the first point I want to point out is our vertex, which is at, what was it? I already forgot. Negative 1.5, comma, negative 20.25, right? So if I go over 1 over a half down to 20.25, it'd be somewhere around here, right? And let's see, the y-intercept was at negative 18, so it's something like this, right there. The x-intercepts were at negative 6 and positive 3, I believe. Now, a couple more facts that I can use in order to more easily locate this parabola is I remember that the parabola is reflected over its own axis of symmetry, right? So it's a mirror image. So if this point is here, and that's 1.5 units away from the axis of symmetry, then another half unit and a 1 unit over here, this point must be here as well. Which is what? That looks like it's at negative 3, comma, negative 18. So I can plot that other point, not having done any math, but just using the fact that I know that my parabola is mirrored over that. And a minimum number of points I'd recommend having to draw a parabola is 5. So you got to have at least 5 points. And our parabola would look something like that, right? A mirror. It doesn't technically come to a sharp point there, so don't be deceived by that. And that's what our graph would look like. Let's see if I open up Sketchpad again real quick, and I go to Graph, New Function, and I do x cubed, nope, squared, plus 3x minus 18, and graph it. You can see I do in fact get the same function there. So we did graph it correctly using our points. Let's see, I'll just move that over there. So yeah, so that's how I can graph these quadratics. So I get all sorts of information I can gather from them and go from there. Now regarding the slopes of this parabola, it wasn't as helpful in this case because I landed on such an odd spot. But it does in fact work out where I could kind of move the up 1 over 1, up 3 over 1 trick, and it would work out because this was a regularly shaped parabola. Now, one quick thing that I want to point out, if I have a problem, all right, just as a general concept, is that, and it's said to solve the following equation, and I have some quadratic like x squared minus 4x plus 4 equals 0, and I want to solve this. I can solve this graphically by 1, replacing 0 with y, 2 is graph it, and then 3 is find the x-intercepts. Now, the reason this works is because think about the graph of the parabola. Y is 0 for the x-intercepts of our parabola here, right? So by graphing this equation and then figuring out where the graph equals 0 vertically speaking, I'm actually finding out the values of x that end up working for it. So this is kind of an interesting trick how you can solve by graphing. However, I'm not a fan of this technique. I do think it's valuable to see parabolas, and it sometimes can answer different questions or word problems, real-life situations, and things like that. But as far as solving graphically, it's kind of an inaccurate technique, because what if these x-intercepts happen to land on weird decimals or things like that? It's not the most accurate way to solve. And as you see, even when I was graphing, I recommended finding our roots or x-intercept by solving algebraically here rather than graphing. But nonetheless, this is kind of a preliminary look at how to graph quadratics, and the names of their graphs are parabolas. All right, well, thank you so much for watching, and I'll talk to you again later.